Hi, I'm Dr. Neenu Garg. In this session, I will discuss deadlock avoidance. Let's start. If we have a resource allocation system with only one instance of each resource type, then we can use a variant of resource allocation graph for deadlock avoidance. In addition to the request edge, this is a request edge and assignment edge, there is another edge which is introduced, which is claim edge. So this edge is a claim edge. It is basically a dotted edge. This edge indicates that a process PI may request resource RJ. Claim edge is converted into request edge when process requests a resource. Means initially in the graph you will see like this. This means a claim edge, and how to interpret it? PI make request for RJ in future, but it has not requested it for yet. When it actually requests for this RJ, then this edge is converted into a request edge, present. Okay. Now PI, this resource when allocated to PI, then the edge is like this. This is the assignment edge. Okay. After PI has used this resource, it will release the resource. This edge will again convert to a claim edge. So after this, the edge will again like this. Because if a process has used a resource, there is a possibility that it may again request for this resource in future. So the resources must be claimed priorly in the system. Means PI, before starting executing, all its claim edges must clearly appear in the resource allocation graph. Suppose that the process PI requests resource RG. Now the request can be converted. If PI request for RJ, then this request can only be granted if converting the request edge, this request edge into assignment edge does not result in cycle in graph. So if no cycle exists, then the allocation of resource will leave the system in a safe state. If there is a cycle, then allocation will put the system in unsafe state. So in case of the assignment converts the resource allocation graph with the cycle, and hence the system is in unsafe state, then the request should not be granted. In that case, process PI has to wait. Okay. Now, in order to understand this, let's take this example which is shown here. In this example, this edge is assignment edge, this edge is request edge, and these two edges are claim edges. It means both P1 and P2 may request for resource R2 in future. But R2 is still free. As you can see in the graph, R2's current state is it is free. Now let's P2 request for resource R2. If you convert this request edge into assignment edge in this graph, it will be like this. That is, if you grant the request of P2, then the edge will become like this. Can you do this assignment? No. Why? If you allocate this resource R2 to P2, what will happen if P1 requests for R1? This claim edge will convert into request edge. Assigning R2 to P2 may put the system in unsafe state, because once the resource is allocated to P2, then as soon as P1 generates a request for R2, the system will go from unsafe state to deadlock state. So let's just summarize quickly that these two are claim edges. So none of these two processes have currently issued request for R2. Let's suppose P2 issues a request for R2. The question is whether the request has to be fulfilled or not. Till now, the system is in safe state. Granting the request of P2 will put the system in unsafe state. Okay. Once the request is granted, the system is now in unsafe state. And as soon as P1 generate the request for R2, the system will turn into deadlock state. So one thing is also proved from here is that all deadlocks are unsafe states. Okay. But unsafe states may or may not be a deadlock state. We see that resource allocation graph method is useful when there is single instance of a resource type. But this method is not applicable if you have multiple instances of each resource type. This thing we have also covered in previous sessions, in which we saw that when there are multiple instances of a resource, then a cycle may or may not be a deadlock, may or may not be a deadlock. So if we have multiple instances of each resource type, we have to use other method, and that method is Banker's algorithm. We will cover this algorithm in next slide. I hope you understand this session. Thank you.